So picture this. It's the turn of the 20th century, and physics is just buzzing with excitement. Scientists knew atoms were real, and they even knew, thanks to guys like J.J. Thomson, that they had these tiny little negative parts inside called electrons. But wait a minute, atoms are neutral, so there has to be some positive stuff in there to balance it out. The big mystery was, how is it all put together? Right? That's the billion-dollar question. You can't just pop an atom under a microscope and take a picture. Figuring this out required some of the most amazing detective work in the history of science. It was all about using clues, indirect evidence, to build a picture of a world that is just impossibly small. Okay, so the first logical guess came from the man who discovered the electron in the first place, J.J. Thomson. Back in 1898, he came up with a pretty simple and honestly pretty reasonable idea for what an atom looked like. He called it the plum pudding model. You can also think of it like a watermelon. The idea was that the atom is this big ball of positive charge. That's the pudding, or the fleshy part of the watermelon. And scattered all through it are the tiny negative electrons, like plums or seeds. It actually made a lot of sense. It was stable, and the positive and negative charges all balanced out. This was our very first real guess. But see, the thing about a good scientific model is you have to be able to test it. And it was one of Thomson's own former students, a guy named Ernest Rutherford, who cooked up a brilliant experiment to do just that. He was actually expecting to prove the plum pudding model right. But what he found instead? Well, it changed physics forever. The experiment itself, which was carried out by his assistants Geiger and Marsden, was genius in its simplicity. They basically built a tiny particle gun. They shot these alpha particles, which are like teeny tiny, positively charged bullets, at a sheet of gold foil that was unbelievably thin, only a few thousand atoms thick. Then they put a detector screen around it that would light up whenever an alpha particle hit it. Simple, right? Now here's where it gets wild. Based on the plum pudding model, those alpha particles should have just blasted right through the gold foil. I mean, the pudding was thought to be so spread out, it wouldn't put up a fight. And yeah, most of them did just that. But some of them were deflected at crazy angles. And a few, a very, very small number, bounced almost straight back, as if they'd hit a tiny, solid wall. Think about that number for a second. Only 1 in 8,000. It was super rare, but it happened. And Rutherford knew it couldn't just be a fluke. He later said it was like firing a 15-inch shell at a piece of tissue paper and having it come back and hit you. The only way a positive alpha particle could be knocked back like that was if it ran into something incredibly small, incredibly dense, and also positively charged. The soft pudding model just couldn't do that. And this quote just nails his conclusion. The atom wasn't a soft pudding at all. Instead, nearly all of its mass and all of its positive charge had to be crammed into this impossibly small, dense core at the very center. He called it the nucleus. So this led to a completely new picture of the atom. Rutherford proposed it was like a miniature solar system. You've got this tiny, super heavy nucleus at the center, that's the sun, and then you have the lightweight electrons orbiting it like planets. This model explained the experiment perfectly. The atom is mostly empty space, which is why most particles flew right through. But if one happened to be aimed just right at that tiny little nucleus, wham, it would get repelled. Now, Rutherford's nuclear model was a huge leap, a monumental step forward. It gave us the nucleus, it gave us our modern sense of an atom scale. But when you started to apply the known laws of physics from that time, the whole thing fell apart. It had 2 fatal flaws. Okay, here's the problem. Problem number 1, the death spiral. According to the physics of the day, any charged particle that's accelerating, and orbiting is a form of acceleration, has to give off energy. This means the electron should be constantly losing energy, causing it to spiral inwards and crash into the nucleus in less than a second. Atoms would just collapse. And problem 2, that death spiral should produce a continuous rainbow of light as it falls. But when we look at atoms, they only emit light at very specific, sharp colors, like a barcode. This model couldn't explain either of those things. The whole thing was a mess. The solution came in 1913 from a Danish physicist in Rutherford's own lab, a brilliant guy named Niels Bohr. He made a proposal that was just breathtakingly bold. He basically said, what if the old rules of physics just don't apply inside an atom? What if we need a whole new set of rules? And so, Bohr laid out 3 new rules. First, he just declared that electrons can exist in special stationary orbits, where they just don't radiate energy. They're just stable. Why? He just said they are. Second, he defined which orbits were allowed using this new, weird quantum rule. He said only orbits with specific, packaged amounts of spin or angular momentum could exist. And third, he said that an atom only emits light when an electron jumps from a higher orbit to a lower one. The energy of that light particle, that photon, is exactly the energy difference between the two orbits. And that third rule, wow, that was the masterstroke. It perfectly explained the mystery of those atomic fingerprints. The reason we only see specific colors of light is because electrons can only make specific jumps between these allowed energy levels. It's not a smooth slide, it's a sudden leap. The energy gaps are fixed, so the colors of light are fixed. Take a look at this table for hydrogen. It shows exactly what we mean. An electron can sit in the ground state at negative 13.6 electron volts, or it can be excited up to the next level, at negative 3.4. But it can never, ever exist at, say, negative 5 or negative 10. It's like a ladder. You can stand on the rungs, but you can't just float in between them. And every time an electron jumps down a rung, it lets out a photon of light with a very specific color. Bohr's model was an incredible success. For hydrogen, it worked perfectly. But there is still this really annoying question hanging in the air. His rules, especially the one about which orbits were allowed, seemed totally arbitrary. They worked, but why? Why those specific orbits? It felt like he'd just made them up. It took another decade for the next amazing piece of this puzzle to click into place. This was the real head-scratcher. Bohr's model was like having the right answer, but not knowing how to show your work. The explanation that finally came was even weirder than Bohr's rules, and it came from a French physicist named Louis de Broglie. De Broglie had this wild idea. What if particles, like electrons, also behave like waves? And he used this fantastic analogy. Think about a guitar string. When you pluck it, it doesn't just vibrate any old way. It forms these beautiful stable patterns called standing waves, where a whole number of wavelengths fit perfectly. De Broglie said an electron's orbit is the same. An orbit is only stable if the electron's matter wave fits perfectly around the nucleus with no messy overlap. And here is the real aha moment. When you do the math, when you take de Broglie's condition for a stable standing wave, you end up deriving Bohr's arbitrary rule about angular momentum. It wasn't arbitrary at all. It was the natural result of the electron acting like a wave. The rule had a reason, and that reason was quantum weirdness. So what a story, right? We went from a simple plum pudding to a miniature solar system to this strange picture of an electron as a standing wave. Bohr's model was a huge achievement, but it was really just the end of the beginning. It was a stepping stone. It only really worked for hydrogen, an atom with one electron. And it couldn't explain why some of those spectral lines were bright and others were faint. To go further, scientists had to completely let go of the idea of electrons as little planets in neat orbits. They had to build a new theory from the ground up, one that fully embraced this bizarre wave nature of everything. And that new theory was quantum mechanics, which is what we still use today. And that, well, that's a story for another time.